Good afternoon, everyone. Welcome to our 6th Environmental Science Seminar series that EPA runs. This one is on electricity generation, challenging for the future, with our special guest, Dr. Jill Caney. I'm Andrea Hinwood. I'm the Chief Environmental Scientist of EPA Victoria, and we run these seminar series on topics of interest to you, but also topics that are important for EPA Victoria. And I guess with my focus, with a particular focus on science and technology and how we use that to actually deal with environmental protection problems as they relate to environment and human health. Dr. Jill Caney, who's joining us today, has an extensive background and expertise in working on climate research and energy distribution, and it's great to have her here today to share her knowledge and insights with us. I'd like to begin by acknowledging the traditional custodians of the land on which we meet today and pay my respects to the elders past and present. I extend my respect to the Aboriginal or Torres Strait Islander people, colleagues, staff and students who might be here today. And a big welcome to everyone who's out there listening to this via our live stream throughout Victoria, Australia and overseas. We're finding that these series are actually attracting global attention, and I'm sure the topic of today with renewable energy will be no different. A few housekeeping notes. Please switch your phone onto silent for the duration of the event, and if there's an emergency, the tones will go off, and follow the instructions of on-site staff, and clearly you'll follow the exit signs. So someone asked me earlier, why are we talking about renewable energy today? And why is EPA Victoria interested in this topic? We're talking about renewable energy technologies and environmental public health impact. It's a topic that's important to us because we need to deal with the unintended consequences of the actions we take to provide energy for the community. And our feedback from actually talking to you is it's a topic that you're particularly interested in as well. We all know that energy is essential to the way that we currently operate in society. And we are now at a point where we really need to consider and be very deliberate about the choices we make about energy and, importantly, the issues for the future. Many of the issues that we're currently facing are ones that we probably didn't consider 20, 30 years ago. But we have the opportunity now, using science and technology and with the way that we operate, to actually make sure we minimise environmental impacts. The Victorian Government, as I'm sure most of you know, is heading towards a renewable energy target of 25% by 2020. Most of that renewable energy production in Victoria is coming from hydroelectric, solar and wind generation projects. Our role at EPA is actually to protect the environment and people from the harmful impacts of pollution and waste. And it's our job to make sure that any new technologies are not impacting the environment and environmental health. We have a new general environmental duty, a new piece of legislation coming in place on the 1st of July 2020. And the focus on that legislation is that we better target prevention in control measures up front so that we don't suffer the consequences of environmental impacts. So we need to absolutely understand the technologies, the environmental impacts, the types of discharges, emissions, waste and management options so we can better control them with our legislation down the track. There have been lots of studies and reviews undertaken over the last few years, and often we hear that wind power, for example, is considered a sustainable renewable technology, and it's widely used. We all know that. But it's also interesting at the same time that we have significant concerns being expressed by communities in terms of the large amounts of land required, what happens to these wind generators at the end of their life, as well as concerns about noise and visual amenity. And of course, there have been recent examples in the media about the issues for endangered species and bird strike in particular. Solar is also considered a good option, but it also has some significant environmental issues during construction and of course the waste at the end of life. We as a society have embraced solar energy production. In my home in Perth, I have a solar hot water system and electricity generator as well. And there are now 2 million photovoltaic installations across Australia. These systems usually last about 10 years. This means the volume of these systems reaching their end of life is expected to sharply increase in coming years. Griffith University researchers recently estimated that around 1,500 kilotons of retired photovoltaic waste will be generated in Australia by 2050. The federal government is currently considering regulating how this particular industry manages its waste nationally to make sure that we don't end up with hazardous substances in landfill and that we actually look at reuse and recycling opportunities. Clearly, this presents a challenge and an opportunity for us. And I think that those of us in Victoria understand this issue quite well. We're currently dealing with an influx of e-waste banned from all Victorian landfills as of the 1st of July this year. And we know that recycling solar cells is not yet in place in Victoria. And battery energy storage systems are currently problematic to recycle as well. Sustainability Victoria are doing a lot of work on this front, and they're leading a national investigation into how end-of-life solar systems can be effectively managed in Australia through product stewardship, and where producers, retailers and consumers have responsibilities for managing environmental impacts. And again, I get back to the general environmental duty that EPA will have in terms of its legislation as of the 1st of July 2020, where there is a responsibility on all duty holders, on everyone, to make sure that the measures are put in place to deal with environmental impacts. So by understanding the current and potential environmental issues associated with renewable energy sources, we can think about the entire life cycle from the products at initiation and at the end of life. Our assessments must be technology specific and place-based, and the benefits of co-benefits need to be clear. So science and technology, in my view, are key to helping us actually achieve our targets in terms of renewable energy and also in achieving better public health and environmental outcomes. So you'll be hearing about some of these technologies today and the challenges in implementing or adopting them. But I want to reiterate, this is a great opportunity for us to actually understand these issues and be much more deliberate in our choices in the future. So on that note, this gives me great pleasure to introduce our guest speaker for today. Dr. Jill Caney is a climate scientist working in energy. She's the General Manager of Networks at Energy Networks Australia. She's facilitating the transition to a low carbon energy future, and she brings a wealth of experience in working with electricity networks to address regulatory and market challenges that need to be resolved to support the reliable and resilient provision of sustainable electricity. It's my great pleasure to welcome Dr. Caney here today. Please join me in welcoming her.
All right, hello everyone. First of all, thank you to the Environmental Protection Authority for asking me to speak today, and hopefully today we will go through a little romp through climate change and energy. So, I'm going to be talking about today climate change. I'm going to give you a little bit of background on climate change, the causes, which I'm sure we all know, the global situation as it is now, and the local situation here in Australia. I'm going to be talking about weather versus climate and the linkage between electricity and weather and how that impacts our generation mix and your role in electricity today. So climate change, or the greenhouse effect, has been known about for a long time. If we didn't have a greenhouse effect, it would be very cold, -18, so sometimes it's a good thing. The problem is the rate at which we're putting greenhouse gases such as carbon dioxide and methane into the atmosphere. Also, water vapour is a key greenhouse gas that we don't talk about. It is the most significant greenhouse gas, and I'm going to talk a little bit later about the hydrogen economy, which may upset the water cycle. And if you like, the greenhouse effect is about upsetting the carbon cycle, and the hydrogen economy may have a negative impact on the water cycle. We don't know. We haven't really started looking at what hydrogen might do. So greenhouse gases allow the sun's incoming radiation to enter the atmosphere, and then the atmosphere traps the outgoing radiation, increasing temperature. It was discovered, if you like, in 1896, so it's not a new thing. We've known about it for a long time. The Kyoto Protocol was signed in 1997 and came into force in 2005, and that's the protocol, and we'll kind of explore a little bit about why that's important, that's supposed to control our use. There's been obviously subsequent agreements like the Paris Agreement about trying to constrain temperature. And I talk about the protocol because we had the Montreal Protocol, which was signed in 1987 and came into force in 1989, and that was to control ozone depleting gases. And we have someone here who knows a lot about ozone. That's Ian Galbally. And I like to talk about the Montreal Protocol because, in fact, that worked. So we, as a global community, we identified a problem and we took global action. Now, the global action that we took was slightly easier to undertake than addressing climate change. It just required a change in the refrigerants that we use. Didn't really require us to cast out our refrigerators and our air conditioners and move completely away from it. But the challenge now with climate change is that we're going to have to change our behaviour. And so that makes it more challenging, but I like to talk about the Montreal Protocol because it tells us that we can do something when we put our minds to it. So this is one of my favourite diagrams. It's called a flying carpet. It's a 3D representation of carbon dioxide in the atmosphere. So it looks really complicated. The colours represent the amount of carbon dioxide in the atmosphere, and to the left side is the latitude with the high northern latitudes at the back and high southern latitudes, so if you like, Arctic at the back and Antarctic at the front. Across the front we've got the year, and up we've got the level of carbon dioxide. So you can see probably most clearly on the bottom edge there's a nice little wiggle in the CO2 cycle. It's more dramatic in the northern hemisphere. If you look, I like to think of it as like hills and valleys. So you can see there are big mountains in the north and we come to a plain in the south. And where you get that transition from the hills to the plain is the equator. So if you like, we've got the northern hemisphere and the southern hemisphere. So the wiggle is due to vegetation. So in the summer, plants are drawing out carbon dioxide from the atmosphere as they photosynthesize, and that shows you the kind of impact that vegetation has. You'll see that there's a bigger cycle in the northern hemisphere, and that's just because there's more land in the northern hemisphere, so there's more trees in the northern, well, more plants in the northern hemisphere. There's not as much land in the southern hemisphere, which is why we don't have such a big seasonal variation. And so the cycles are also anti-correlated, so they're opposite because we have winter and summer at different times. And I guess you can clearly see that carbon dioxide has been going up. The other plot on the right shows the increase in extreme weather events. So climate change is believed to be impacting weather, and we'll tease out a little bit the difference between weather and climate change in a little bit. We have more extreme events which tend to now be more costly, and that's really a factor of the fact that we're kind of encroaching more and more into the natural environment. So we're kind of closer to the coast, we're closer to the bush, and so the potential for impact is greater. We have greater exposure. So now we'll talk a little bit about Australia. The picture in the top right corner is the Cape Grim Baseline Air Pollution Station in Tasmania, which I had the pleasure to run for 6 years and was probably the most impressive office view I will ever have. I'm afraid the view from my office in Melbourne isn't anywhere as good as the view I had in Tasmania. Cape Grim is part of Australia's global climate reference station. It receives clean background air from the Southern Ocean, essentially Antarctica, 30 to 40% of the time. It's part of the World Meteorological Organization's Global Atmosphere Watch program, and it was one of the first 5 sites that commenced measurements in 1976. So we've been monitoring atmospheric chemistry at Cape Grim for over 43 years. Part of its role is to monitor compliance with the Montreal and Kyoto protocols, but it also measures a whole suite of other atmospheric species, including rainwater chemistry, particle size and chemistry, particle numbers, and also radiation, so solar radiation, direct and diffuse. So it's a very important site. It's quietly beavering away and has been for 43 years. The scientists at CSIRO help with the chemistry program, and the Bureau of Meteorology looks after running it. So what I have here is up to June 2019, this was taken from the CSIRO, is the CO2 plot. You can see that there's that little wiggle, seasonal cycle. You can see that it's going up. We're over 400 parts per million. And there was a time when I was running Cape Grim when I said if we went over 400 parts per million, we were in trouble, and we're already there. I should have shown you a picture of a CFC, and you would see that that has peaked and is coming down. So we can make a difference. We've just got to take those steps to make a difference. All right, so let's explore weather and electricity. So you and I, we use electricity. This is a pie chart that shows the average demand for a household. Obviously, when it's hot, we use more electricity because we're cooling, and when it's cold, we use more electricity for heating. And I used a dog and a cat just in case. You'll have to try and guess whether I'm a dog lover or a cat lover from this picture. And you can see that over 50% of our energy use is related to heating and cooling, water heating. Here in Victoria, that will be a mix of electricity and gas. And we'll kind of come back to this again when I explore domestic scale or behind the meter batteries. The average annual use is around 8,300 kilowatt hours. I'll try and explain what a kilowatt is in a little bit. I'm also trying really hard not to use too many acronyms, so do tell me off if I drift into using a lot of acronyms. So the other thing, and this is another picture of demand. It's slightly stylized, but you can see the blue curve shows a morning peak in demand. It dips in midday, in the middle of midday, and then it peaks higher in the evening. You can also see in the yellow, that's where solar generation peaks, typically at midday, right where we don't want it. It's no help for us for evening demand. And I guess the lower plot shows that this upper plot in the yellow and green shows you the perfect cloud-free, which it obviously always is in Australia, and probably particularly in Queensland. Cloud-free, what you might expect with no clouds or no aerosol, whereas the lower plot shows you the impact on solar generation as a cloud moves through. And you can see that you very quickly lose solar generation, and that is a challenge for the electricity system to manage. And I guess wind isn't always blowing, so that's another thing to manage. In the old days, generation was just chugging away, and it was independent of weather. So the system operator, or the Australian market operator, AEMO, only really had to think about forecasting what you and I were going to do, how much electricity we were going to do, and then they'd tell the generators to dial up to meet that. Now they have to also use weather forecasting to help them predict what generation they're going to have, as well as how we're going to respond to today's weather, and that makes it much more complicated. I should note that coal generators, like humans, don't particularly like extremely hot days, and gas large plant don't like extremely cold days, which is not really a problem that Australia has to worry about. Now, one critical thing is that generation must exactly equal demand to keep our electricity system stable and secure. So if you think of water, and that's called frequency, we have to control the frequency. And frequency is important because all generation synchronizes to it. If you like, all generation in the Australian electricity market has the same heartbeat. And it's all going at the same beat. And if we change that heartbeat, that has consequences to system security, which is a way of saying it has consequences to keeping the lights on. So if you like to think of frequency, if there's any electrical engineers out there, please, I'm going to apologise. Think of it as water pressure. So if you start, you've got a pipe of a fixed size, which is your wire, and you're going to send water down the pipe. If you send more water down the pipe, the pressure increases, and that's frequency will increase. And in an electricity sense, it might get a bit warm, your wire might get a bit warm. If there's more demand for water than we can supply, we start pulling it out of the pipe faster than we're putting in the pipe, and so pressure drops, and that's a drop in frequency. And so we have to try and keep, that's the market operator's job, is to try and keep frequency at a nice stable level. That's the 50 hertz you might have heard about that we have in our electricity system. And I'll come back to that in a little bit. Now this is weather having another impact on the electricity system. It obviously, our infrastructure is out there. Sometimes it's undergrounded, particularly in the CBD, but our infrastructure is exposed, and so this shows a transmission tower following the black grid in South Australia in September 2016, where a number of transmission lines were impacted by tornadoes. So ensuring that we have a resilient electricity network is one of my key interests. I am particularly interested in when bad weather attacks electricity networks, because that allows me to bring, my climate interests, my weather interests, and my energy interests all together. But what we build today, these assets are typically 40 to 60 years long. They last for a very long time. So what we build today is going to be experiencing a very different climate and weather in 40 to 60 years' time. And yet we don't really, at this particular point in time, when we go, because electricity networks are highly regulated in order to ensure that you have a fair price for your electricity. But when we go to the regulator and say, well, we need to build a stronger tower because in 40 years' time, it might not be up to the job, the downward pressure on prices may mean that we might not get that extra strong tower. And it brings us to the tricky question of what should customers today pay for a benefit that those customers might not see in the future. So that's a tricky question that we have to deal with. But if we want a resilient and secure electricity system in the future, we do have to think about that question. So the electricity system is very fragile. This is taken from the UK, and this is what's called TV pickups. So this is taken from the royal wedding of April 2011. And on the left, in the blue, you can see the demand as it was actually on that Friday. It was a public holiday in the UK. And in the pink is Good Friday in the same year, which was obviously another Friday public holiday. And you can see that there are significant differences in the demand that was expected on the day. Now, when the wedding was announced, the system operator in the UK kind of put together like a whole, war footing office to try and manage this, because TV pickups are essentially where major events ensure that everybody is doing exactly the same thing and has a major impact on electricity. The plot on the left shows frequency across the bottom, which is what I was talking about with water pressure. And you can see there that there were major drops in demand. Basically, no one in the UK was moving when Kate arrived at the Abbey. We were all sat in front of our televisions. And then we kind of went, oh, thank goodness for that. And we all got up, we made a cup of tea, and we went to the toilet, which means that we turned on our kettles and started using electricity. And in the water system, water pumps had to turn on in order to move water around to fill the kettles and flush the toilets. And that's very prosaic, but that is how it works. Now, I'd just like to point out that the balcony kiss, again, we all sat down and waited for the big kiss on the balcony. That decrease was 3,100 megawatts. That's the equivalent of taking 2 Hazelwoods out of the system in demand. And you cannot turn off a coal-fired power plant that quick. So you have to have a great deal of flexibility. And this is actually someone in the National Control Room in the UK sitting at a console with the television, watching it happen, bringing things on and off as it happens. That is what goes on behind your light switch and behind your PowerPoint. It can't all be automated, not for this kind of thing, because these are random events. We don't know when the balcony kiss is going to happen. We have to have someone sitting there thinking, okay, it's happened, and now I'm going to have to bring in some more generation, or now I'm going to have to take it out. That is how fragile the electricity system is. So we're going to talk about 2 major events in Victoria. This is Australia Day 2018 and 2019. These were extremely hot days. We lost power for 2 very different reasons. In 2018, there was extremely high demand. It was at that point a record. It was obviously beaten again this year, and that was due to air conditioning load. And medical research shows that you're 77% more likely to survive an extreme heat event with a working air conditioner at home, and extreme heat is Australia's biggest killer. So it's important that we have electricity to keep us cool. There was, on the 28th of January, enough electricity to meet that demand. You can see in the table that we wanted over 9,000 megawatts of demand, and there was 10,500 megawatts available. The problem was that we were trying to shove so much electricity down the wires that the protection equipment that we use, the surge arresters and the fuses, they are activated to keep us safe because you don't want your lines to get too hot. And as a result, 95,000 people lost power. On the 25th of January 2019, again, it was extremely hot. We had another record for maximum demand. And the problem this time was that we didn't have enough generation. There was an unexpected failure of a power station, which meant that the market operator had to direct what's called load shedding, which means people were cut off in rotation for an hour at a time to ensure that frequency remains stable. Because if frequency in the whole system, if frequency in Victoria goes bad, it affects New South Wales, it affects South Australia. So these events are infrequent, but are likely to become more common with climate change. But peak demand at these levels only occurs a few times a year, if that, and so it is prohibitively expensive to build a network for just these isolated occasions when we have exceptional demand, because we wouldn't use those assets rarely, they'd just be sitting there. That capacity would be sitting unused. So we need to think about other ways to manage these kind of events, and we'll explore that later. All right, so we're still in the steam age in Australia. We're still boiling water to make electricity and using steam to drive turbines. And the steam age started in 1698, so we've been doing it for quite some time. It's not particularly efficient, but it's not terribly inefficient. For instance, a solar PV panel is about 11 to 22% efficient at converting the sun's energy into electricity. Wind's a bit better, at converting wind energy into electricity. That's about 50% efficient. Most efficient generation that we have is hydro generation. And I'll talk a little bit more about that in the next slide. And I just wanted to quickly mention nuclear power, because that's been in the paper recently. Again, that's just boiling water. It's not terribly sophisticated. We're just using the heat to boil water. So generation is changing. And it's changing in response to climate change, and it's largely the result of incentives to change generation. But it is now much cheaper to build a solar PV or wind generation station than a conventional combustion plant. Most of you will know about wind and solar PV. They're kind of mainstream now. There's solar furnaces where you use the sun's energy to boil water, and then you use the steam to make electricity, so it's kind of just like what we just talked about. And we've seen that the sun and the wind are variable, so we've got to do something to ensure that we can meet demand. Interestingly, there are a number of generators exploring putting solar and wind together. As the graph in the top right shows, you've got that solar peak in the midday, but often, and the easiest one to explain is the right-hand peak in green, which is wind farm output. So like sea breezes, the changes in the temperature impact the kind of wind we see, and together you get a smoother output than separately. Of course, as Andrea said, all generation comes with environmental issues, so you have to explore the advantages and disadvantages. We've heard about waste. Coal and gas are still significant generators in Australia, but we've got greenhouse gases and particles which cause health effects. We've got wind with impacts on birds and bats, and also sound. And then we've got land use issues. We haven't really, in Australia, explored land use with solar PV, because most of the solar we've got in Australia, although that's changing, is on rooftops. But in the UK, a lot of solar was ground mount. And there were huge discussions about whether we should be using agricultural land and putting solar panels on it. You can lift a solar panel up and still have farming underneath, but obviously if you're taking the sun's energy on a panel, it's not hitting the ground to grow grass. So, and also hydro electricity generation is very dependent on rainfall. And as Tasmania discovered in 2015, if you don't have enough water in your upper dam, it gets complicated. And you have to explore other forms of generation. So hydroelectricity generation, I'm sure you all know, this is our oldest low-carbon generation. It's been around for a very long time. And this is where you drop water onto a turbine, which then spins a motor that makes your electricity. It's one of our most flexible sources of generation, because you can hold the water back and you can drop it. So largely those peaks that you saw in the UK around the royal wedding, they were managed by the UK's hydro generation fleet, which is only just over 3 megawatts. So it was only just capable. So you have to have other flexible assets. By adding a lower lake at a hydroelectric plant, you create hydroelectric pumped storage. So you essentially allow the water to flow through and make electricity, store it in your lower reservoir, and then you pump the water back up, typically overnight when there's not so much demand, so that it's back in the top dam and you can go again. And so this brings us to storage. So how important is storage? We would never think of running a water system without storage. We totally understand that rain is seasonal, and so we must collect and store water for times when there isn't so much available, and sometimes that doesn't work because of drought. Energy storage is not new. I've got some examples there of energy storage. We've had coal piles doing a really good job of storing energy for us for years, wood piles, petrol tanks, and the maybe soon to be extinct hot water tank, because we're moving towards continuous water heating. But the hot water tank is a very powerful source of flexibility in the electricity system. It can provide what's called foot room, which is where, if you imagine in the middle of the day, we have all that solar, we can't find enough demand for it. So foot room is when you turn something on and use that spare energy, and hot water is one of those things that we could do. So electricity storage is slightly harder. You need batteries or pumped hydro, but there are many other different technologies. For instance, there's liquid air energy storage, which is where you use electricity to compress air and you store it as liquid nitrogen, and then you re-expand it through a gas turbine to make electricity. There are capacitors, there are flow batteries, there are many different technologies. But typically batteries are short duration, as you will all know with your mobile phones. And so the challenge is ensuring that your battery is in the right state of charge when you need it and managing that. But storage can help fill the gaps or manage peak demand. So remember that evening peak. Even if a battery could do half an hour to an hour, that might be enough to get us over the top of that peak. But this is, I guess, so now I'm going to talk about behind the meter batteries, which is all the rage at the moment. So does it really matter where storage is located? And this table compares and contrasts. If you wanted to deliver a 1 megawatt frequency response, which is to make sure frequency is stable, you need to provide support. If we were to aggregate domestic batteries, typically there's only a 24% response rate. That means if we ask customers to do something, only 24% of them will do it, because maybe the battery's not in the right state of charge, or it's their battery, so they should be using it for what they want to use it for. So that means that instead of just having a 1 megawatt battery, you actually need to have 4.2 megawatts of battery to deliver 1 megawatt to allow for that 24% response rate. That's roughly 800 batteries at a cost of around 12 million. Because you're going to have to send a signal to all of those batteries to do something, it's slow, because you've got to have that time for the response. The people looking after batteries at home, and I don't mean to be rude, are what I describe as inexperienced. You know, I have enough trouble making sure my mobile phone is charged when I want it, but I would struggle to manage a 5 kilowatt battery at home to ensure that it was exactly where I wanted it, so that I could use it to operate my lights or my equipment at home, let alone support the system. There's some question about, if I'm providing a service to the Australian energy market operator, who's going to pay for the costs and maintenance and looking after that battery to ensure that it's in the right condition? And also, I've just mentioned, so I've got that thermal storage, which is the hot water tank. That can just sit there. It has an inversion heater in it. Someone just presses a button and it starts using electricity and it starts heating up water. When you look at a utility scale battery, and this is not necessarily owned and operated by a utility, it could be a community battery. There are some really good examples. There's a really good example in Western Australia at Alkimos Beach, where it's used like a library. Instead of everyone having a battery, they use a larger battery that someone else looks after for them, like a library service. So they pay a subscription, they can put in and take out of the battery as they need it. If you've got a single battery, it's 1 megawatt, it's being looked after by a third party who's hopefully an experienced person. It can provide a very rapid response. Because you've only had to buy 1 megawatt to deliver 1 megawatt, it's less expensive. And I've got asset base, so if a utility, i.e. a network, operates the battery, it goes on to the regulated asset base. But I guess if you want to manage your energy costs, if you can think back to that really colourful pie chart that I put up earlier, a battery is going to struggle to help you with your heating and cooling costs, because the equipment that you need, an air conditioner or even an oven, are high energy use devices. Your battery won't last very long, but as I said, it might last long enough to help the system over a difficult patch. What we really need is, on a hot day in Australia, PV generation is at a peak, and so we should be using our air conditioners and we should be using our homes as thermal energy storage. But unfortunately, building standards don't necessarily mean that we have buildings that are able to store hot and cold. So even if we pre-cooled our homes on extreme heat days, probably most of that cooling would have dissipated by the time we got home in the evening. But it would have done a better job than just leaving the house quietly baking in the sun for us to come in and stick the air conditioning on and have to cool the house a really big distance. So, for instance, there are things called virtual power plants, which is where domestic batteries are aggregated together. There's a number of trials going on in Australia, and a virtual power plant in South Australia had hoped that on Australia Day 2019 that it would be keeping Victoria cool, but unfortunately lots of the batteries were not in the right state of charge. South Australia, however, did help. It was importing into Victoria, and that's kind of, we'll come back to why that's important later. So diversity and connecting different regions together means that hopefully we're not all experiencing the same sort of weather, and we can share our resources. Okay, so other technologies. Other technologies, so the picture on the right, that is a 6 megawatt battery in the UK. It's not terribly exciting. It's just lots of black boxes in a big room with a big air conditioner. And I'm afraid even when I first started at Cape Grim, I thought it's going to have lots of exciting equipment, and it was just lots of boxes with digital displays, and indeed batteries are pretty much the same. So we've talked about our energy use and demand, but demand is going to change. So, you know, we're making some of our own electricity, but also if we start using new technologies like electric vehicles, that's going to place increasing demand on the electricity system if we go and plug our cars in. So electricity networks and the market operator are very concerned about us all getting home on a hot day, turning on the air conditioning and plugging in our 3 electric vehicles all at the same time. How will we meet that demand? However, you can have smart charging where you might plug it in, but someone else will manage when it actually physically charges, and maybe it will do that overnight so that in the morning it's ready. Although you have to park your car somewhere when you go to work, if you're not using public transport like I do. And so you could charge your car in the middle of the day, which is exactly when we have that big peak in solar that we want to do something with. And then there's hydrogen. So we could have hydrogen cars. We could replace the methane that we use for cooking and heating with some amount of hydrogen, and we would use electricity to split water to create hydrogen. Currently we get most of our hydrogen from hydrocarbon processes, so it's not exactly green, but if we were using electrolysis and using renewable energy to do that, we could get green hydrogen. You have to ask, is that what we should be doing with our excess electricity that we're trying to manage? You then have the option to store the hydrogen and move it around to where you need it. And it could be used in vehicles. There are hydrogen vehicles, they're quite common in the UK, but like electric vehicles, they need infrastructure, charging infrastructure or refueling infrastructure. The attraction with hydrogen vehicles is they have a longer range, they're much more like how we currently use our cars, so it's not such a big behavioural change, and it may be, hydrogen is probably more suitable for freight, trucks and buses, so if they need infrastructure, that infrastructure will be there. Some of you who are old enough will remember Betamax and VHS videos, and there was a big competition about which type was going to win, and it ended up being VHS, which had a brief moment in the sun, and then we got DVDs, and then we got Blu-rays, and now we don't have physical media at all. It's all in the cloud, and we use Netflix. So if you like, this is the problem with technology, is that it's changing so rapidly, and yet it's hard to predict, and so hard to plan, and electricity networks and the market operator need to try and understand what you're all thinking and what you're all going to do in order to ensure that the electricity network and the electricity that you want is there, whatever decision you make, and that is a big challenge. So I just wanted to talk a little bit about climate change versus air quality. So typically, burning fossil fuels results in particles because coal and hydrocarbons are long chain. They have a lot of carbon and a lot of impurities. They make all kinds of exciting stuff, some of which is not good for us. The transition to gas, which is just a single carbon with 4 hydrogens hanging off it, so methane, means that there are a lot less emissions. So gas has 1/3 of the emissions of coal. And we'll come back to that again. So monitoring and mitigating climate change largely focuses on greenhouse gases, although particles and clouds do have a role because they get in the way. They will reflect incoming radiation, although some types of particles will absorb incoming radiation, like black soot. So it's not straightforward, it is complicated. Whereas managing air quality has largely been about particles. Most of our Clean Air Acts arose from smogs in cities in the early industrial period. And the size of a particle influences where it ends up in your lungs, and that's really why we're concerned. And those of you who are keen photographers might have noticed that the atmosphere is clearer after rain, and that's because of what we call wet deposition, which literally washes particles out of the sky. There's also dry deposition, which is just that particles are heavy and gravity has an effect and they kind of fall out of the atmosphere. But you can have an impact on climate change by improving air quality, although improving air quality is less likely to have an impact on climate change. Sorry, improving climate change is less likely to have an impact on air quality. So in Europe, there was something called the Large Combustion Plant Directive, which was designed to reduce sulfur dioxide and nitrous oxide and particle emissions from coal plants in Europe. This had a huge impact in the UK, where the number of hours that a coal plant could run had a hard cap. And once you reached your hours, that was it. You couldn't run anymore. So this drove the UK away from coal, but the UK already had a strong presence in gas. But it was even difficult in the UK because the transition away from coal was faster than expected, because at that particular time it was cheaper to buy electricity from coal-fired plant than gas-fired plant. So if you like, the coal plant burnt through their hours quickly, and the UK government had to deal with a winter shortfall in generation. It was likely that there wasn't going to be enough generation in winter, and so they developed a capacity market, which is perhaps not an ideal market solution, but it shows that market solutions drive behaviour and the way we use our system. So for instance, here in Australia on the 21st of July at 1:15 p.m, the wholesale cost of electricity in a 5-minute period was 0. So that means electricity was free. But I mean, it was going to be it's been wiped out by everything else, and that was largely because there was a lot of wind generation on that day and demand was low. It was a Sunday. But this is a problem, because if electricity is free, why would you build a big generation plant? If you can't make money generating electricity, why do you invest in it? So the problem is we're all making our own electricity. It makes it harder for bigger generators to make electricity, but we won't always have enough electricity to meet our own needs, so we do need some big generation to help us. All right, so I'm going to compare and contrast Australia and the UK, but let's not talk about what happened overnight in the cricket. And those of you that know me know that I like my cricket, so I'm a bit sad today. These charts show the generation mix at the large scale. And this is today. So you can see on the left, we've got Australia. Total demand is 35 gigawatts. That's a big number, I think. That's the equivalent of 17.5 million kettles. It's kind of silly numbers. The UK has approximately the same maximum demand. But you can see that in Australia, the 54 gigawatts is the total maximum amount of generation we have to meet that 35 gigawatts, whereas in the UK, they have 90 gigawatts to meet their 34 gigawatts. So if you like, they've got a nice comfort zone there of lots of extra generation. And also the UK, being an island, is highly interconnected with the rest of Europe. So if the UK doesn't have enough electricity, it can call on its neighbours, and we'll come back to that in a bit. Now you can see that still in Australia, 70% of our generation is coal-based, whereas you can see in the UK it's 5% is coal, and gas is much more significant, and wind. And we also have a significant amount of hydro. We also have nuclear power in the UK. Sorry, that's the 19% is nuclear power. And so the UK have been hoping to build a new nuclear power station at Hinkley C, which is the site of a current nuclear power station. The price that the UK government are paying for that electricity is £90 per megawatt hour, which is approximately $160 per megawatt hour for new nuclear. In Victoria, the wholesale price last week was $79 per megawatt hour. So if you like, new nuclear is twice as expensive as our current generation mix in Victoria. So if your argument is that you want to bring down prices, you want cheaper electricity for customers, new nuclear is not the answer. Even before you get to considering the fact that it will take over 10 years probably to bring in or plan and build a nuclear power station, and our coal fleet is not going to last probably fully that distance. But again, nuclear is just boiling water, making steam, and it's also not very flexible. It just sits there and chugs away. So you have to have this foot room service overnight when demand is low to use up that nuclear electricity. More modern nuclear power stations are slightly more flexible. All right, so the generation mix small scale. So this is going to be all about solar PV. And the top picture is a glorious summer day in the UK. And the bottom picture is a glorious winter day somewhere in Melbourne. And what I guess I wanted to say here is that Australia likes to think that it's doing a fantastic job with solar PV, but actually the UK is doing better than you. It makes me so good to say, it feels so good to say that. And I mean, the deployment rate in Australia is very rapid, but we have more solar large scale, total and on residential rooftops in the UK, even though the conditions in the UK are not exactly ideal at 52 degrees north compared to Australia. So if you like, Australia has a huge resource and could be doing more with it, with the issues that I've mentioned before in terms of land use, if you're talking about ground mount. But in the UK, the reason I've got a star against the 2.5 gigawatts is in March, the UK ended its feed-in tariff scheme because in its view, solar panels were now a rational thing to invest in for householders. However, what they have done is they will be bringing in retailers are now required to buy excess electricity from domestic properties. So if you like, you and I are selling electricity into the wholesale market that retailers buy rather than I'm being encouraged with a feed-in tariff to deploy solar. And so you should be, well, I guess using solar allows you to address your energy costs, because if you're making electricity at home and using it at home, you're not importing as much electricity from a retailer. And this brings us to the tricky issue of how we pay for our electricity networks, which is based on the amount of electricity that we import. So if you have solar PV, you're not buying as much because you're making your own electricity, and so now you're not paying as much to look after the electricity networks that you and others are connected to. And we're not allowed in Australia to charge, we're not really allowed, it's not allowed in the regulations to charge anywhere for export to use the system. So it's a bit like if our data for our phones and computers, we don't pay for upload. We just pay for download, whereas in reality is we pay for both download and upload for data, but in the electricity sense you would only pay in one direction. And this raises issues of equity, not only around how we use the system, because fewer people are paying to keep the system operational, but also those that are renting or those that can't afford to invest can't share in this new technology. Grants in Victoria are helping with this, but community projects and co-ops are another way you can facilitate other people having a role in renewable energy or local energy markets. So, for instance, putting solar panels on schools and council buildings and allowing people to invest in that allows them to share in this energy revolution that we're experiencing. So the electricity system is changing. In the old days, generation was made at the left and it flowed down to us on the right. And today we're making electricity on the right and we're sending it back up the electricity system. And this is what we call reverse power flows. You may have heard that nice technical phrase used in the media. Now the transmission network, which is the big transmission towers, that can go in both ways. That's like our freeway. It's designed to take electricity and go in both directions. The distribution network, which is what you and I are connected to, is designed to go in one direction. If you like, it's a highway, a major road, a minor road, and your driveway. Now, if you imagine trying to get a truck up your driveway in the opposite direction, that's one of the issues. And I like to use the analogy of a car. A car can go backwards, but it only has one gear to do so, while it has many gears to go forward. The distribution electricity system can go backwards, but only for limited periods. In the same way that you wouldn't want to drive in reverse from the CBD to Hyatt, you wouldn't want your electricity system to run backwards for any length of time. And our networks have protection equipment such as fuses and surge arresters, and those were the things that operated to protect customers on that first Australia Day incident in 2018. And transformers are not designed to go backwards. And if you were driving backwards in your car, the road signs and the traffic lights, you'd be looking at the back of them, and they wouldn't be providing the same level of safety as if you were going forwards. There are newer styles of equipment that can handle this reverse power flow, but we need to invest in that. But us customers, we don't want to pay more for our electricity. We're very keen that we keep our electricity costs down, and so investment is regulated. All right. So I've talked a little bit about how do we manage our system going forward. We don't want to build a network for those odd occasions when we have incredibly high demand, because that wouldn't be efficient. So we need a basket of options. So you'll hear a lot in Australia about firming. We need to firm renewables, and that's a very generation-centric view. It's about ensuring that we have enough generation, whereas I prefer to think that we should, as a very generation-focused thing, whereas we should be thinking about demand and trying to use electricity when the generation is there, because that will have cost benefits, such as the foot-room service being paid to turn on. And I prefer to think of flexibility services. So we need to be more flexible as customers. So we've talked about, there are 4 sources of flexibility, and we've talked about storage that can help us over short-term peaks in demand, and it can provide foot-room by when you charge it. It also can do a lot of other technical services that help the system stay stable. It's often described as the Swiss Army knife of the electricity system, because it can do so much. Because you can get, for that one investment, you can get lots of benefits. There are flexible generation technologies like gas engines and diesel gensets. They have air quality issues and noise issues, but if you're only going to run them for those short periods of peak demand, perhaps that's okay, perhaps that's manageable. And then I talked about interconnection, which is largely a connector, a transmission line that goes over a boundary. It might be a state boundary or it might be an international boundary, but it allows us to have diversity in where we get our electricity from. So you can imagine that Tasmania is going to be colder when it's hotter in Melbourne, and so Tasmania can export electricity to Melbourne to keep us cool on a hot day. And I talked about how South Australia was supporting Victoria on the last Australia Day heatwave. The problem comes if the whole of the southeast of Australia, which has happened, is experiencing the same heatwave, and Adelaide, Melbourne and Sydney all want air conditioning at the same time. So finally, one source of flexibility is demand response. This is you and I matching our demand to the generation that's available. And you can be paid for providing demand response. It's very common in other countries. It's just that we haven't really developed it here in Australia, and it's only just getting started. There was a new rule proposed a couple of weeks ago that you may have seen covered in the press. And it's about turning up or turning down at the request of the network or the market operator to help avert a problem. So if we look at that really hot day, imagine if we all turned our thermostats up on our air conditioner just a couple of degrees, so that perhaps we're not all at 21 degrees, we're at 23 degrees. That aggregated drop in demand over all of Victoria might just be the difference between us having a power outage and load shedding and us keeping the electricity flowing. And indeed, in New South Wales last summer, they ran a social media campaign to ask people to modify their thermostat settings. It helped on a number of occasions, and it was altruistic. There was no payment for that service. It was just people making sure that things worked on a tricky day in the electricity system. So it is up to you. The plot at the left is a breakdown of electricity costs by state, and that's in the national electricity market, which isn't national because it doesn't include the Northern Territories and Western Australia because they're too far away. And it's broken down by the use of network, the 2 networks, and the various other charges. But surveys indicate that we are very concerned about the cost of our electricity. However, studies also show that we're actually not that excited by electricity because we very rarely change our retailer. So we like to moan a lot about the electricity price, but we don't actually do anything about it. We also expect to be able to connect whatever new technology we like to the network and in our homes whenever we want to do it, and we hope that the networks and the market operator will facilitate that. But investment will be needed in order to deliver the infrastructure that we need for the future, for the things that we want to do, the way we want to go. And so we have to have an active role in shaping our own energy use and developing the energy system of the future. We can't just be that passive customer at the bottom of the system hoping it will all be all right. We do now actually have an active role in the energy space. So climate change and energy are inextricably linked, and this is my final slide. So climate change drives how we generate electricity, and it drives how we use electricity. It's increasingly complex to manage the changing electricity system, and I've talked about some of the issues today. Climate change will impact the resilience of our electricity system, how we plan our electricity and what we hope that it will withstand in the future. And because the assets are so long-lived, we have to think about how we're going to fund them and who is going to pay. Do we pay now for someone else in the future to have a better experience, or do we expect the future person to pay? And flexibility is absolutely key, and this is where us, the customer, has a role, and how we can help deliver a low-cost, secure and sustainable electricity system. So you have an active role. Thank you.
So, we have some time for some questions. So, does anyone have a burning question they'd like to ask?
So do you need me to repeat that question? Or so basically, how far behind is Australia in using demand response? I'd say very far behind. So in the UK, they've had a program. They've always used demand response to keep the system stable. In fact, the royal wedding, some of that was hydro, but that was industrial and commercial customers turning up and down rapidly to support the electricity system, and that's a paid-for service. It's called short-term operating reserve. They do frequency control, so that's keeping everything stable. The pressure in the pipe stable is also through demand response. And the electricity system operator in the UK in 2015 started what was called the Power Responsive Programme, because it had determined by 2025, I think it is, that 60% of all of the system support services that it uses will come from the demand side. That's very developed. The US is probably quite developed as well in the demand side response, as is Europe. It's just not something, we just want to use electricity. We don't want to, turn it up and down. We do have large-scale demand response, aluminium smelters, basically. We turn off a pot on a really tight day, but we don't ask smaller customers to get involved.
Thanks, Jill, for a great talk. And just another comment, I actually think Power Shop is offering a residential scheme at the moment for and they'll SMS you up to 2 days in advance, and you get a $10 little credit voucher.
Yeah, and United Energy, which is one of the distributed network service providers, has been exploring demand response for a long time to manage peak.
What I was going to ask you, I heard that Germany, in the north, there's a lot of renewable energy production, and in the south there can be a lot of demand increased at certain events, and that the system, the engineers are sort of troubling about the solutions around that frequency change and how to handle it. Are we sort of in Australia about to face the same sorts of challenges, and is the solution going to be similar to Germany or different to what Germany's had to facilitate?
So frequency control is a very tricky thing. Currently with what we call large synchronous plant, i.e. a coal-fired power station, you have these great big turning metal turbines which provide what we call inertia. So they slow down the system's response to a problem and keep the frequency much more stable. So if you like, you can imagine you're pedaling a bike. If you want to go uphill, you start pedaling faster a bit before you get the hill so that you don't lose any of your speed. And so inertia and the large coal plant that we have provides us with, if you like, a cushion of stability. Obviously, as coal-fired power stations shut down, which is what's happening in Germany and in many other countries, you lose that synchronous generation. If you like, it becomes harder to keep the heartbeat consistent throughout the system. There are a variety of technologies to resolve that. One of them is batteries, which respond really quickly and can inject energy quickly. There are many complicated things like synchronous condensers, one of which is being deployed in South Australia to support the network by Electranet, the transmission network service provider over there. But they're expensive solutions, and we don't really want to have synchronous condensers sprinkled all over Australia. So we have to start thinking about how we're going to keep the system stable as our generation mix changes.
Final question.
I just have a question in regards to whether there's something in the future or now working with the federal government and maybe the way we build infrastructure as our population increases to help facilitate reducing our energy use, like the materials we use or how we build housing as we build like infrastructures up and have more people in them. Is there anything like that?
I guess there's critical infrastructure approaches, and that's through the UN. So the Sendai framework talks about resilience, and for instance, every dollar that you spend on resilience saves you roughly $4. It depends largely on the sector that we're talking about. But we tend to, in most countries, Australia is not alone in this, we wait for the bad thing to happen and we respond, and that tends to be more expensive than if we reduce the risk before it happened. And obviously then it's very difficult to show the benefit, because the event that you avoided, it's hard to cost that event that you avoided because it didn't happen. I guess, and the other issue is that we have in Australia, and this is common again globally, we have a Department of Energy and Environment. They don't necessarily talk to the Department of Building Services or the other departments. So standards are critical for how we deliver a flexible future, that that's important in terms of how we build our buildings, and we have a housing crisis, so there's a lot of pushback when you say we want to build houses that are passive or energy efficient. Construction companies may say, well, that's expensive, I just want to bang up lots of properties as quickly as possible. But the government departments are not talking to each other necessarily about, should we be facilitating better insulation, thermal mass, etc., so we can store heat and cold, depending on where you are in Australia. You might not want to store heat if you're in Queensland. You might want to, you've got to think about all of these things, and the problem is we don't. Together, we think about them separately, but we don't join it all up.
Yeah.
And largely, there are very few people that operate across all of those kind of sectors.
Is there any foresight into that happening in the future? Because that just seems like pretty much your only option right now.
I guess the closest I can get is in the UK, they took climate change outside of government parliamentary process. So they have the Climate Change Committee that set carbon budgets and kind of set the destination to which the UK is travelling, and it is independent of whoever is in government. So if you like, the government can change, but there's always that overarching, destination that we're going to. But even the UK are struggling with how you make everything fit for purpose. And then we have the retrofitting. We have a large amount of building stock and a lot of things in place already. how do you make them fit for purpose as well?
Well, I think all of us would agree that we didn't necessarily think that we'd hear about the royal wedding and the implications for the way that we actually behave and how that actually influences our electricity use and all the rest of it. I think what our presentation today has demonstrated, though, is how interconnected energy supply, planning, environmental protection, public health, all of those aspects of the way we live are all interrelated, and we actually do need to consider them up front in a more holistic way. And it seems to me from hearing is that one solution is not going to be the answer, that it will be multiple solutions depending on where you live and what the particular mix might need to be. And of course we need to think about that, particularly in Australia with the drying climate, increases in bushfire events and extreme weather events, etc. So I'm sure you'll all agree this has been a great presentation. I've certainly learnt a lot. I'm sure you have too. We will continue this conversation. We have another environmental science seminar series coming up in November where we're actually going to talk about behaviour change. I also think that is also related to these topics that we're talking about today. Thank you very much for coming today. Please join me in thanking Jill for a great presentation. Hopefully we'll see you next time.